basically covered, sorry, gotta get my pen going. We basically covered this material on Friday, and we got into the very beginning of the conservation equation, and we'll get deeper into it today. And in particular, we'll talk about a simplified solution of the conservation equation, which we call ideal chromatography. And we have ideal chromatography when we can make two assumptions. When axial dispersion is completely negligible, and when we can assume that the solute in the moving phase and in the stationary phase are in complete equilibrium. Those two conditions hold. There are really no broadening factors going on inside the column. So you get what we call ideal chromatography, and there's no broadening. This is not a very interesting situation, since there's no such thing as a perfect packed bed. There's always some longitudinal diffusion, there's always some eddy dispersion, and there's always some resistance to mass transfer, either in the moving phase or in the stationary phases. But this at least sets one limiting case for us. So we'll then immediately get into the situation where we allow there to be slow mass transfer, either in the moving phase or in the stationary phase, or both. Sometimes one is negligible compared to the other, but we do have to consider the possibility of both kinds of rate limitations, outside the particles and inside the particles. It turns out that even though we're taking a very mathematical approach here, the solution to this problem turns out to be identical to the Giddings-Eyring solution. And so I'm not even going to write that nasty equation with the modified first-order Bessel function in it again. We're just going to assume that that's the solution, and we'll look again at the first moment and the second moment, and of course the HETP. And we'll consider both the case of external mass transfer and the case of internal mass transfer as the rate limiting processes. So that's what we're going to cover today. Here's where I got to on Friday. You just saw the equation. So let's go through it term by term. The term on the left is the product of the axial dispersion coefficient dAx, and the second distance derivative of the concentration. So it's a diffusion looking like term because it depends on the partial squared C partial Z squared. So it acts like diffusion, but the dAx is not just a diffusion coefficient, it's a flow dependent coefficient. The first term on the right is the product of the interstitial velocity and the first distance derivative of the concentration, and this corresponds to the net effect of convection into the zone and convection out of the zone. So that's the convective transport term. Terms C and D added together are the net accumulation of analyte in the zone in the column. This term C, partial D, is the accumulation of solute in the mobile phase. C is the mobile phase concentration. And Q is the stationary phase concentration. So the D term, and this is the D term, is the net accumulation of material in the stationary phase. Now the epsilon here is not epsilon E, it's not epsilon I, it's not epsilon total. It's something that is called the porosity ratio. And if you do the mass balance properly, you'll find that what it is actually is the ratio of the volume of stationary phase per unit length of column divided by the volume of mobile phase per unit length of column. So it's really Vs over Vm. The per unit length of column cancels out. And this is really our friend the phase ratio from week 1 of the course. So it's the phase ratio. And that's what we chromatographers would call it. But since a lot of this stuff was done originally by the engineers, they call it the porosity ratio. I don't know why they do, but that's their lingo. And if you read the papers, you got to know what it is, because they may not tell you. So this is the differential equation that governs everything that's going on inside the column. Now, if we, first approximation we'll make is we're going to neglect axial dispersion. So we're going to turn off longitudinal diffusion, and we're going to turn off eddy dispersion. Get rid of them. And so this term disappears, it becomes 0, and that greatly simplifies the problem because we no longer have a second distance derivative to deal with. So we're neglecting both longitudinal diffusion and eddy or hydrodynamic dispersion along the axis of the column. Now, the next assumption we're going to make is we're going to assume full equilibrium of the solute between the two phases. That is, we're saying that C and Q are not related kinetically, they're related by an equilibrium expression. So we're going to set Q equal to Kc, plug it in there, and when we get done doing that, we're going to have this equation, and we have epsilon K times dc dt, so there's a dc dt, there's a dc dt, so I can factor that, and so this equation becomes the same as that equation, and this is our retention factor. So K prime equals epsilon times K, where epsilon is essentially our phase ratio. So this is now the problem that we're solving, and it turns out that this has an extremely simple solution. It says that the concentration as a function of distance and time will be equal to the input function of time times this function u. The argument of u is is t, minus z divided by ue divided by 1 plus k prime. This function u is known as a unit, hence u, unit step function. It's really a very, very simple function. If we have u of some argument, lambda, when lambda is less than 0, the unit step function is 0. When lambda is greater than or equal to 0, the unit step function is 1. 0 as of the argument, it discontinuously goes up to 1, and it stays there forever thereafter. So if we plot the unit step function, this is what it looks like. And here's my concentration. Here's time 0. So the unit step is 0, stays there until the argument is greater than 0. It undergoes a step up to 1, a unit step, and then it stays there indefinitely. So that's a unit step function. That's what this function looks like. So, whenever t is less than that, the argument is 0. The unit step evaluates at 0. You have something times 0, 0. When t is equal to or greater than z over this stuff, the unit step goes straight up to 1 and stays there for all times greater than that number. And the concentration then is this function of time times 1. So you got to know this function of time. So what this says is you have to define the input function to the column. And once you know the input function, you can just move it through the column. Now, I'm going to take the simplest case, which is a pulse function. So we're going to assume that this is a pulse, a rectangular pulse. So here's what happens. This is the concentration. This is axial distance. There's my pulse function. And here's t equal to 0. There's a pulse at 0 time. As time progresses, this rectangular pulse is simply pushed down the column, and it retains its exact shape. That's what this is saying, that the shape of that never ever changes as the pulse moves along the column. Well, let's think about our assumptions. We said that there is no axial diffusion, there's no axial eddy dispersion, and the solute remains in perfect equilibrium between the mobile and stationary phase. All of the broadening factors that we've been talking about have been taken out of the problem. So this is what absolutely has to happen. There is no broadening. You can easily show that that pulse is going to come out of the column at time tr. Now, if you have a non-porous column, that is, the particles that you pack in the column have no porosity at all, the stationary phase is merely on the very outside of the particles. In other words, you've got perfectly solid particle, and you've got an extremely thin film. This is not a core shell, this is just stationary phase around the outside of that. So T naught then would be the dead time of the column, would be the length of the column divided by the interstitial velocity. So the retention time would be T naught times 1 plus your retention factor. On the other hand, if you have a porous particle, be it a core shell particle or a fully porous particle where the pores go all the way throughout the whole particle, then the retention time is going to be Tm times 1 plus k prime, where Tm is the length of the column divided by the velocity u sub m, where this is the percolation velocity of the mobile phase through the column bed. And the peak shape is going to be identical to however you shoot the stuff into the column. So if it goes in as a rectangular pulse, it's going to come out as a rectangular pulse. If you have a poor injector, either in LC or in GC, whatever the shape of that pulse is, as it loads into the top of the column, that's exactly what it's going to be when it gets out of the column and gets to the detector. So again, this is the solution to the ideal chromatography problem. And it's pretty boring. At least the retention times make sense. Okay, now, the first interesting situation is we're going to leave the biaxial equal to 0. So there's no diffusion along the axis, and there's no eddy dispersion caused by the flow heterogeneity in the axial direction. But we're now going to remove the equilibrium condition. So Q is not going to be equal to Kc anymore. We're going to assume a first order kinetic relationship between the stationary phase and the mobile phase. So dq dt is equal to some rate constant Kb times K, the equilibrium constant, the partition coefficient, times C minus Q. Now, if you're at equilibrium, Q is equal to Kc, dq dt is 0, you're in steady state when you're at equilibrium. That's the boring situation that we just went through. But we're going to assume now that Kc is not equal to Q. Now, Kc could be greater than Q or less than Q, depends on which part of the peak you're talking about. The front of the peak, Kc is greater than Q. The rear of the peak, Q is greater than Kc. If we take this and superimpose it on this and solve the two equations simultaneously, in other words, I'm not assuming this one, I'm taking this and assuming the kinetic relationship, then the solution of this problem is exactly the same as the Giddings-Eyring problem that we did a few days back. I'm not going to repeat it. Of course, the first moment is the same as the Giddings-Eyring first moment. Assuming porous particles, the first moment is the retention time is equal to Tm times 1 plus K prime. The second central moment is what we call sigma squared of the column. That will work out to be 2K prime over gamma times, whoops, that should be Tm squared, where gamma is this back rate constant, and Tm is the dead time of the column. So gamma is a dimensionless rate constant. I can derive from there the plate count, and then finally from the plate count and length I can get to the equation for the HETP. And this equation is exactly the same as the equation that Giddings and Eyring derived. Remember the K prime over 1 plus K prime squared relationship, the interstitial velocity, and the backward rate constant. In the Giddings-Eyring derivation, we called it the KD, the dissociation, the desorption constant. This is the reversed rate constant. Now, this model doesn't require us to assume what process corresponds to this rate constant KB. We could be talking either about mass transfer in the moving phase or mass transfer in the stationary phase. We can talk, and to put it another way, we can talking about mass transfer external to the particle or mass transfer limitations internal to the particle, or both. So let's think about our particle. Here's an attempt to show a little more realistic picture of the inside of a particle, of a porous particle. So all of this stuff here is pore volume. Okay. The solute molecules, the analyte molecules, are trying to get from the outside of the particle in the moving phase to the outer surface of the particle. That's this surface. And then they're trying to transport through the pores of the particle. Now, transport outside of the particle, here in the moving phase, since that phase is moving, part of the transport mechanism, at least part of the transport mechanism, is convection. Once a particle arrives at the outer surface of the particle and enters a pore, there's no longer any convection. The pores are typically so small, 60 angstroms, 100 angstroms, a really, really wide pore in special particles made for big molecules might be 1,000 angstroms. Might be 1,000 angstroms. 1,000 angstroms is really tiny compared to the size of the particle. You cannot get flow inside of a pore that is that small. Maybe if you had a 10,000 angstrom pore, you could get some flow in it, but not much. The pressure drop across a particle, across a single particle, is not sufficiently large to drive fluid, viscous fluids, through a tiny pore like this. So the only mechanism for transport, once you're inside the particle, is diffusion. So outside the particle, we have convective transport and we have diffusional transport, simultaneously, if you will. But inside the particle, we basically only have diffusion. Now, one of the earliest models of transport in flowing material is what's called the Nernst boundary layer theory. And that theory says that the fluid right near the surface of the particle is stagnant. And if that fluid is stagnant, then the only way to get through it is by diffusion. So there's convection out here, but once you get within some very thin layer of the surface, you have transport that's limited by diffusion. So again, once you're within this dashed line, even though the dashed line is a little bit wider, a little bit further out than the surface of the particle, you have the diffusional transport. Once you get to the surface of the particle, you now have stationary phase diffusion. You can have diffusion in the liquid or the gas, whatever is inside the particle. You also have diffusion along the surface of the particle. Molecules can diffuse on a surface. It may not be fast. Sometimes it's really slow. I mean, really slow. Sometimes it's almost, but not quite as fast as diffusion in the bulk fluid. It depends on exactly what kind of chromatography you're doing. In reverse phase chromatography, where the stationary phase is a nonpolar substance, diffusion on the surface is actually fairly fast. In ion exchange chromatography and in normal phase chromatography, where the surface is very, very polar and the mobile phase is less polar, diffusion on the surface tends to be slow. And sometimes even negligibly slow. But you still have diffusion in the space that's filled either with gas or with mobile phase liquid that's stagnated inside the particle. Okay, so back to our friend the Nernst layer. And just a pictorial representation of what's going on is here's your solute concentration, and here's distance from the particle surface. Particle surface is distance 0. This is what I mean by the particle surface right here. We're talking about diffusion in this thin film here, and then out here in the bulk, we assume that convection is so fast that the solution is homogeneous. Out here, the solution is homogeneous, and you have only a diffusion gradient between the Nernst layer and the surface of the particle. And so that's the plot versus distance from the surface. And that's our bulk mobile phase, which we assume is well mixed because it's moving. One of the key notions of the Nernst diffusion layer is that the faster the fluid is moving, the thinner this region of stagnated fluid is. So if we could increase the flow rate a lot, then the plot would look like that. If we make it thinner, then diffusion through that zone takes place faster, and the system is closer to equilibrium, and there's less void. Okay, so we're saying then that dq dt is proportional to some rate constant for transport through the boundary layer times the difference in concentration of the solute between the surface of the particle and the outer Nernst layer. So this is the concentration at the Nernst layer, the outer edge of the Nernst layer, and this is the concentration right at the surface of the particle. Now if we look at the units of this, we have concentration units here and concentration units here, but we have inverse time dependence here. So Kf has units of time to the -1. I'll take that as having units of seconds to the -1, just like a normal chemical reaction rate constant. So you should think of this as a rate constant. If you have a spherical particle, you can relate this chemical rate constant to a mass transfer coefficient and these have units of distance per unit time. So I'll represent that as centimeters per second. Now if we check this out, We say this is units of centimeters per second. Oops. And this is your particle size, your particle diameter. It has units of length also, centimeters. So it's centimeters per second per centimeter. The centimeter cancels out, and we get the right units for the KF part of this. The reason I have to go through this hocus pocus is that the chemical engineers are the people who measured these rates. And they don't use rate constants, they use mass transfer coefficients. And they've come up with some ways of estimating KMT. Since we care about KF, we have to know how to convert KMT to KF. And for a sphere, this is the relationship. Now the Chemie people don't actually work with the mass transfer coefficient directly. They work with another one of these dimensionless numbers. This is the so-called Sherwood number. Let's check the units. We got particle size, so that's distance. We got KMT, that's distance per unit time. So we got length squared per unit time divided by a diffusion coefficient, which of course is units of length squared per unit time. This is the dimensionless quantity. It's really the ratio of how fast things are moving by convection relative to how fast they're moving by diffusion. If the Sherwood number is high, then transport is dominated by convection. If the Sherwood number is low, then the transport is dominated by diffusion. So one of the Chemie relationships gives the Sherwood number as a function of the Schmidt number and the Reynolds number. We talked about Schmidt numbers and Reynolds numbers a few days ago. This particular correlation is known as the Waco correlation. What Waco did was study packed beds, all sorts of packed beds. Packed beds where the fluid was a gas, packed beds where the fluid was a liquid, packed beds where the tube was a pipe, literally a pipe. Packed beds where the tube was maybe a few inches in diameter at the narrowest. I assure you we never did anything we would care about. But nonetheless, all the results are presented in terms of these dimensionless groups, and a dimensionless group is dimensionless, so it doesn't matter what the scale of the system is, this should describe it. And this is Waco's correlation. There's something like 2,000 data points in here for different size tubes, lengths, gases and liquids, high viscosity, low viscosity, high density, low density, all sorts of things, and he fits the curve. And this is what he comes up with. Now this may look like a good fit, but this is a log-log plot. 1, 10, 100, 1,000, 1, 10, 100, 1,000. This is a pretty big, wide distribution of points on a log-log plot. It ain't as good as it looks. And one of the big problems here is that for analytical chromatographic purposes, this is about what we care about, where there isn't much data. Now, other people have done other studies under other conditions, and they've come up with, I'm sorry, I'm going to skip that and get right to it. This is Waco's result. Rice and Fu recommend this correlation. Notice there's a little difference here, not a big difference. and there's some difference in the numerical coefficient there. Csaba Horvath, one of the big guns of HPLC, came up with his own correlation. He drops the 2. He says that coefficient is more like 3.4, not 1 point something or other. And he says that that exponent's more like 1/3. One of the absolutely very most popular correlations for the Sherwood number was gotten by Wilson and Giancopoulos. Giancopoulos is a former U of M faculty member, so this must be the right one. But it is really, in terms of popularity of use, this is the most popular correlation. You can see it's similar to the Horvath in those terms of exponents. This has an epsilon E factor in it, and if we take 1.09 and divide it by epsilon E for a typical random packed bed, these two coefficients are not very different. Which one is right, I really don't know. This is how they plot up. This is a log scale. I kept the reduced velocity. I'm not using Reynolds number now, I'm using reduced velocity. But I kept the reduced velocity in the range of where a chromatographer would care about it. And these are typical reduced velocities, a little bit above the optimum. This is generally above your optimum reduced velocity in LC and GC. But you can see there's a big discrepancy between these two and these two. This is the Horvath and the Wilson-Giancopoulos relationships. These seem to be used a lot more, so I'm going to stick now with the Wilson-Giancopoulos. Not that I have any reason to believe that it's right. So, if I now take the flow dependence inherent in this Reynolds number to the 1/3 power, and combine it with this equation for the HETP in terms of KB, relate the KB to the KMT to the Sherwood number, plug everything together, then sometime later, out comes what we call the external or mobile phase resistance to mass transfer. And the flow dependence, the velocity dependence is hidden in this term. It works out to be the 2/3 power of the velocity, not the first power of the velocity, because of the dependence of the Sherwood number on the 1/3 power of the Reynolds number. K double prime is this combination of the two kinds of retention factors, the regular chemical retention factor and K naught, the retention factor due to the existence of pores in the stationary phase. So if you have a non-porous stationary phase, K naught is 0, the second term is 0, and K double prime equals K single prime. But a lot of the time, 99+% of the time, we're dealing with porous materials, either core shell materials or fully porous materials. The core shell has a lower K naught value than the fully porous material, of course. The K naught this is, I showed you this the other day, is the ratio of the volume inside the particles to the volume of mobile phase outside the particles, and that works out to be this combination of epsilon I and epsilon E. So we can calculate what K naught is going to be. Remember, epsilon I typically well, for a fully porous material, about 0.3, epsilon E for a randomly packed bed, about 0.4. So K naught always works out to be less than 1. The value of a half is pretty big. Let's suppose we have no chemical retention, K prime is 0. Then this term is 0. This is 0, but we have 1 times K naught. So K double prime would be on the order of 0.5 or less if we have a fully porous material. If we have a core shell material, it would be lower. So what this is saying is that even if you have no chemical retention, because the molecules can penetrate into the pore, this term is not going to be 0. K double prime's smallest value is finite. This is the way it plots up. This was K prime. That's K prime, because I've got a curve here with K prime 0. And I think I took K naught equal to 0.5 for this plot. So here's K prime of 0, 1, 3, 10, 20. You see it's approaching a limit. If K prime is greater than about 20, you don't see much difference anymore. The more retention, the more resistance you have in the station, from the external transport. Take a look at these numbers here. Not bigger than 1. Not bigger than 1. And also, you see that these are curves. They're not straight lines. It's because the equation tells us that it depends upon the 2/3 power of the reduced velocity. So it's got to plot up like a curve. This does not, however, approach the limiting value with reduced velocity. It just goes up and up and up and up with the 2/3 power of the velocity. It just never quits. But it does reach a limit as the K prime gets bigger and bigger. Now, thank goodness the internal problem is a lot easier to deal with, because the internal problem is purely diffusive. There's no convective help inside the particles. So this solution of this reduced plate height inside the particles is simpler. The 1/30th comes from the assumption of a spherical particle. If you were to pack the column with cylinders, something else would be there. It's been worked out, but I don't care what the answer is, because I'm not going to pack a column with cylinders. Chemical engineers have packed columns with things that look like saddles that you put on a horse, with toroids, with all sorts of things, and they've worked out the numerical factor. We don't care about them. If you were chemi, you'd worry about it, I suppose. Notice the dependence now on K double prime. There's only a first power of K double prime in the numerator, but a second power in the denominator. This is going to give us a very different dependence. Then we've got the ratio of the diffusion coefficient in the mobile phase to the diffusion coefficient in SZ. That's not a typo. My finger didn't stutter. That is called the stationary zone diffusion coefficient. And that includes diffusion in the mobile phase that stagnated inside the particle, as well as the surface diffusion along the surface of the particle, inside the particle. And there's the good old reduced velocity again. Various people have derived the stationary zone diffusion coefficient, and it works out to be this equation. Here's the obstruction factor for diffusion in the stagnated mobile phase. SM means stagnated mobile phase. Phi is the fraction of the pores that the analyte molecule can fit in, which means it goes from 0 to 1. If it doesn't fit in any pores, then all you've got to worry about, that means that there's no stagnated mobile phase. Gamma S is the obstruction factor for diffusion on the surface, on the interior surface of the stationary phase. K prime is your normal chemical retention factor, and ds is your diffusion coefficient in the stationary phase, on the surface of the stationary phase. And dm is your regular diffusion coefficient in the mobile phase. Gamma S and gamma SM can only be obtained by doing the experiment and fitting the data. There really are not decent theories about this at all. There are theories, but they vary very widely in their predictions. This is the fraction of the pores that our solute can fit in. And here's the result of the calculation. Here's the reduced plate height, reduced velocity. These are straight lines. They are straight lines because there's no convective help. And I'll leave it there for now, because we're about out of time.